Hello, this is question 3 from the 2021 maths. The degree of a polynomial is the highest exponent that appears among its terms. For example, 2x to the 6 minus 3x squared plus 1 is a polynomial of degree 6. Part 1. A polynomial px has a turning point at 0, 0. Explain why p of 0 equals 0. Well, because it goes through 0, 0. And why p dash of 0 equals 0. Right, okay, because there's a turning point there. And explain why there is a polynomial q of x such that. Okay, right, well, let's write down those first two bits then. So we've got p of 0 equals 0 because p of x passes through 0, 0. And then we've got the first derivative at x is 0 is equal to 0 because there is a turning point at 0, 0. So that's good so far. And then we need to explain why there is a polynomial q of x such that p of x equals x squared q of x. So we'd be saying then that p of x won't have any x to the 1 or x to the power 0 terms, which is, yeah, what we're going to get off of these two things that we've just said. So off of the first part, if it's going through 0, 0, then the coefficient of x to the power 0 is going to be equal to 0. And we can also say that the coefficient of x to the power 1 is equal to 0 because we've got a turning point there. So therefore, p of x equals x squared q of x. Right, part 2. Polynomial r of x has a turning point at a, 0, for some real number a. Write down an expression for r of x that is of a similar form to the expression above. Justify your answer in terms of a transformation of a graph. So we can move our turning point then from 0, 0 to a, 0. So we've moved it off to the, well, it could be left or right, but we're doing an x minus a on this, aren't we? So we can say r of x equals p of x minus a. That's just to do our transformation of a in the x direction. So that means that we're getting r of x then is going to be x minus a squared multiplied by q x minus a. That's our r of x. Is that what I wanted? Write down an expression for r of x similar to that. Yes. Okay. Right, part 3. Storming along here. You are now given that f of x is a polynomial of degree 4. It has two turning points, a0 and minus a0 for some positive number a. Write down the most general possible expression for f of x. Justify your answer. So it's got a double root at a and a double root at minus a. So justify your answer would be interesting on this, but anyway, let's put down double root. I mean, maybe this is the justification. I'm not sure what else you need to say really. Double root at x equals a and at x equals minus a. And I mean, you can stretch it by some amount in the y direction and can be stretched in y direction by some amount. We're going to have some multiplier. So therefore f of x is going to be equal to, well, let's say a times, well, x minus a squared for the double root at x equals a, and x plus a squared for the double root at x is minus a. That's that one. Describe a symmetry of the graph of f of x. Prove algebraically that f of x does have this symmetry. Well, we're going to have a reflection in the y-axis, that's going to be fine, isn't it? Because we've got it at plus a and minus a. Right, reflection in y-axis. So i.e. f of x equals f of minus x. So let's put that into this then. F of minus x is going to be a minus x minus a squared times minus x plus a squared. Take a factor of minus 1 from each one of those brackets, so that is going to be a times minus 1 squared times x plus a squared times minus 1 squared times x minus a squared. So that is a x plus a squared x minus a squared, which is equal to f of x. Part C, write down the x-coordinate of the third turning point of f of x. So we've got some graph which is looking, well, either it's doing a turning point there and a turning point there, in which case if it's symmetrical we'll have another one there, or it's doing the negative of that. I mean, it could be either way, but we're going to have to be we don't have to justify our answer on that one, so we know it's going to be x is 0, x equals 0. I mean, this is to do with symmetry again. We've just said that it's symmetric about the y-axis, so it's going to have to be when x is 0. Right, so that's done part 3. New sheet up. Part 4. Is there a polynomial of degree 4 which has turning points 0, 0, 1, 3 and 2, 0? Justify your answer. So we'd be getting something that is looking 0, 0, 1, 3, 2, 0. So let's do the positive version. So we'd have something like that. And it needs to, well, if we're going to translate that in the x direction, then we need to have these roots evenly spaced, don't we? Because they were before. It would now be symmetrical about the middle turning point. So let's justify then. So if we translate, what did they call that one? F of x in the previous part. If we translate f of x in x direction, then we've got symmetry about the line, where are we? X is 1 is the middle one. So yeah, x equals 1. That's good, which this works with, which we do have, so that's fine. So therefore this is okay. This is okay, or this set of turning points is okay. Right. Part 5. Is there a polynomial degree 4 which has turning points 1, 6, 2, 3 and 4, 6? So, well, they're not evenly spaced because we've got 1, 2, 4 for x direction, and they're not on, oh, they've moved both of these up to 6. So we've translated transformation in y direction. So that means we've gone up 6 here, up 6. Transformation maybe of f of x in y direction. And in x direction, but we need symmetry about line x equals 2, which we don't have, which isn't the case for these turning points. So we had points. So part 4, we had a big yes, that there is a polynomial of degree 4, and in part 5 we got a big no. And that's the whole question. That was a very quick question 3, but there wasn't really that much to get bogged down on this either. there's not a whole load going on. Once you've set up that initial part in part 1 here, and you've got that expression, and then we're just doing some fairly simple transformations. So I would say that was a pretty friendly question 3 compared to other papers.